Okay, let's say let log of x be equal to t, for example, but my Hagoromo chart just broke, and this also breaks my heart pretty crazily. Okay, don't break Hagoromo chart. A huge thanks to my Patreon supporters for making this episode possible. Mathematicians, welcome back to another video. Don't forget to check out stemmerch.com. We got engineering clocks and merchandise and a bunch of other STEM related stuff, so check it out. Our fractals are pretty freaking amazing. Today we would like to do some more analytic number theory. I'm pretty excited because in less time we have continued to do analytic number theory, even though you didn't really notice that I didn't do so, because we are working towards an absolute monster and we are basically about to slay it in some video coming out next week probably. It's going to be amazing. It's probably going to be like 1 hour long, but it's fucking fantastic, trust me. But today we would like to get ourselves another representation for the so-called Digamma function. If you don't know what I'm talking about, link to the number theory playlist as well as those 2 videos where I derive stuff are down there in the description. So check it out if you don't know about this stuff, alright? That right here, Euler macaroni constant, that right here, Digamma function. And we would like to find out Gauss representation for the Digamma function today. It's pretty useful, it's pretty Gucci, it's an integral representation, and yeah, we're going to dive right in. And it's actually pretty easy to derive if we have those 2 at hand already, and we do. So it's just straight through calculations, and yeah, it's probably kind of obvious that it would come in handy to plug the value for the Euler macaroni constant into here, alright? I mean, it does make sense. Both have upper and lower bounds from 0 to 1. Also, incidentally, we have 1 over 1 minus x here as a common denominator, so it's just going to be like oil sliding down our throat. Okay, Euler macaroni, tasty, going downwards really nicely. Let us dive right in. So if we were to plug the Euler macaroni constant into here, we are going to get the Digamma function with respect to z, being hence nothing but, okay, we are going to get negative the integral from 0 to 1 of 1 over 1 minus x plus 1 over the natural log of x, and then I'm going to write everything out, dx plus our integral from 0 to 1 of 1 minus x to the z minus 1th power over 1 minus x, integrate with respect to x. And here you might notice we can make use of the linearity of the integral to bring those 2 integrals together into one, okay, both integrated over x and from 0 to 1, etc. pp. So let us bring everything together into one big old integral from 0 to 1 of, let's start off with this factor because it doesn't have a negative 1 in front, so 1 minus x to the z minus 1th power over 1 minus x, and then minus, okay, minus into here using the linearity of the integral gives us negative 1 over 1 minus x, and then negative, don't forget to distribute the negative sign into here too, 1 over the log of x integrated with respect to x. We don't want to stop at this point because we can actually do a few more calculations. I mean, that's a valid integral representation. This does work out. Also, we were allowed to bring those 2 integrals together because, well, Euler macaroni is already a convergent constant. It converges to the Euler macaroni constant, what we have here, this integral representation. And for the real part of z being greater than 0, I think it shall be strictly greater than 0. This also converges, so we can bring those together. But we would like to go a step further here, and we would like to introduce a certain substitution because we would like to turn this into an integral from 0 to infinity. We are going to need this later, hence the new substitution I'm going to introduce, let. Okay, on the one hand, we could get just rid of the logarithm of x. Okay, let's say let log of x be equal to t, for example. But my Hagoromo chart just broke, and this also breaks my heart pretty crazily. Okay, don't break Hagoromo chart. But the thing is, if we just do this right here, we are going to get weird upper and lower bounds, or at least a weird lower bound, because if x approaches 0, then log of x is going to go to negative infinity, and it's weird to have an integral from negative infinity to 0. We don't want that. How can we get rid of this problem? Well, by putting a negative sign in front of the log of x. We have used this trick several times when dealing with the gamma function. Okay, now we can do a few more calculations here and a few more manipulations. So on the one hand, if we were to multiply both sides by -1 because it's not equal to 0, we are going to get that log x is nothing but -t, and raising both sides to base e is going to give us that x is hence nothing but e to the -t, and we can differentiate this really nicely. So doing implicit differentiation, we are going to get that dx is hence nothing but negative e to the -t dt. And well, this is way better because we can now plug this information into here, and the upper and lower bounds are going to be really spicy. So if log x on x goes to 0, we are going to get negative infinity, it's positive infinity. Okay, so an integral from infinity to log 1 is nothing but 0. Okay, now we are going to get 1 minus. Okay, on the one hand, this is something I also want to cancel out. You see, we have 1 over 1 minus x minus 1 over 1 minus x. This is going to die in the corner somewhere. So we are going to get rid of this, meaning overall we are going to be left with negative x to the z minus 1 power, but x is nothing but e to the -t, leaving us overall with e to the -t, okay, with a negative sign in front of it, but the whole thing to the z minus 1 power over 1 minus e to the -t. Okay, just plug in everything into here. And last but not least, negative. Okay, negative and negative is going to cancel out because we are substituting negative log of x, leaving us with plus 1 over t. And what's our differential exactly? This is hence nothing but negative e to the -t dt. Okay, one good thing is we can actually get rid of our upper and lower bounds, so this weird order, by just distributing negative sign into here, giving us an integral from 0 to infinity, so meaning our Digamma function of z is hence nothing but an integral from 0 to infinity of, what are we going to get here? I mean, we have a negative sign in front, so we are just going to switch those two around. Okay, just have the positive part in front, it looks better. Also we can put the e to the -t onto here. Also you might want to use parentheses here. Okay, just to not confuse this multiplication. So we are going to get e to the -t over t. And also we are going to get a negative sign. Okay, on the one hand we are going to have e to the -t times z minus 1. It's going to give us overall e to the -t times z minus, and minus is going to become positive, so plus t. Also we are going to multiply it by e to the -t over 1 minus e to the -t. Integrate with respect to t. And one cool thing is, if we were to multiply those e's together, we are going to get those two to cancel out, leaving us overall with the Digamma function being hence equal to the integral representation from 0 to infinity of e to the -t over t minus e to the -tz over 1 minus e to the -t dt. And this right here is Gauss representation for the Digamma function. It's really useful, looks good. I mean, it's exclusively with respect to those exponential functions. Also, you might notice strictly speaking, we can split this integral up into 1 from 0 to infinity of this part minus this part, because this right here is going to be our exponential integral, but this right here doesn't converge on those upper and lower bounds. So you have to be careful. You have to leave this together for it to converge. But yeah, overall we are going to have a difference. If everything converges, we are going to have a difference once again of diverging series, you could say, diverging integrals, you could say. It's kind of interesting because this right here is nothing but our exponential integral, basically minus a shifted exponential integral. This is what you call this right here. If you don't know what I'm talking about, I have made a little series on exponential integrals, sine integrals, cosine integrals, etc. Other than that, thank you guys for watching. If you did enjoy this little complimentary video, then please like, subscribe and comment channel if you like. It's going to be fun. Quite soon we are going to slay this big boy. And up until the next video, I'll show you guys a Flammy day. Don't forget to check out STEM merch. Ciao!